Hello scholars, you are welcome to the 2026 JAMB and Waec Chemistry Masterclass. And in the course of this class, we are going to look at the topic stoichiometry. So do well to stay with us as we are about to start this class. So we are about to start. Hello scholars, you are welcome to the day 4 of the 2026 JAMB and Waec Chemistry Masterclass. And in the course of this class, we are going to look at a very important topic which most students believe to be a calculation topic. But here the topic is divided because we are going to cut across several topics which we have looked at before. So in the course of this class, we are going to look at this topic which is stoichiometry. And it's a very important topic. Like I said, it has to do with a lot of calculation with some few or minor theories. So try to get your writing materials and also get your friends to join this class. So you can do it to get the link, the live link from your screen, and then share it to your friends, and also get your writing materials so that you can get the very best out of this class. And if you are just joining me for the very first time, my name is Michael Warren, and I'm the lead tutor at Warren Science Academy. And if you haven't subscribed to this channel, do it to click on the subscription button just beneath this video lesson so that you can always get access to my videos whenever I upload any new video. And in the course of this class, if you have any question, comment or suggestion, do it to leave them in the comment section beneath this live video as I always go back to check if there are questions, comments and suggestions. So we'll begin this class by looking at this topic, stoichiometry. So what's stoichiometry? Most persons may ask. Now every word we have has a root or has an origin. The word stoichiometry is coming from a word which is stoichion. So this word stoichiometry is derived from this Greek word which are stoichion and then metron. This word stoichion here means element, and then the word metron here means major. So if we put these words together from the origin, it simply means element measure, or from the back we can say the measure of element. So in stoichiometry we are actually measuring. But what are we measuring? That is the question. Are we measuring money? Are we measuring foodstuff? No, what we are measuring here is element. But what exactly in this element are we going to measure? So before we do that, we must ask ourselves, what is element? Now I want to talk about element. Elements are chemical substances, as we know, that can take part in a chemical reaction, but they will still retain their identity. So let's take that definition. So for element, we know that elements are what? Chemical substance. So elements here we know are chemical substance which can take part in a chemical reaction and still retain the identity. Now, just to add to the definition for element, we also define element as substance that cannot be split by an ordinary chemical process. So in addition, we also know that elements are chemical substance, so chemical substance that cannot be split by an ordinary chemical process. So this definition, both of them talks about elements. So we want to talk about elements. First of all, elements are chemical substance that cannot be split. Split means they cannot be divided easily by just any chemical process. So we can't just take an element like hydrogen, for example, and say we want to just split this substance easily. So it's not something that we can do by an ordinary chemical processes. There are complex processes that will help us to split this element. Furthermore, elements are also chemical substances which can take part in a chemical reaction. For example, during the formation of water, we need hydrogen, which is an element. We also need oxygen, which is an element. So these two guys will combine, or they will react to give us water. So when we talk about element, they take part in a chemical reaction and still they retain their identity. Now let me give you a good scenario. A man and a woman, they are like elements. So the man comes, the woman comes together, and then they get married. Even when they get married, the man is still a man and the woman is still a woman. So before marriage, the man was a man. Even after marriage, the man will still be a man. The woman is a woman. Even after marriage, will still be a woman. Not because of marriage, things in her will change, or things in the man will change. So that is just a simple illustration of what elements they look like. So elements are chemical substance. Number one, we cannot split them by an ordinary chemical process. Secondly, they can take part in a chemical reaction just like a man and a woman. And when they do so, they will still retain their identity. So hydrogen is still hydrogen. It has all its property. Also, you see oxygen, it has all its property. So now let's come back to our topic, which is stoichiometry. Like I said earlier, stoichiometry is derived from this Greek word, which are stoichion and metron. Stoichion here means element, and we've just defined element. Then metron means measure. It's coming from the word metric, and metric also means measure. Now, in chemistry, when we study element, we can study element in two ways. Take note of this. We can study element either qualitatively or quantitatively. So let's take note of that. Now, so in chemistry, that study is what we call analysis. So analysis can either be, analysis can either be a quantitative analysis, or it can be a qualitative analysis. So these are the two forms of analysis. Either is quantitative or it is qualitative. Now, what's the difference? That leads us to the question. Now, quantitative means quantity, and quantity means how many or how much. So we are asking ourselves how many or how much. So this is what leads us to this topic called stoichiometry. So in stoichiometry, what we are doing is a quantitative analysis. We are asking ourselves quantity, how many or how much. But in qualitative, we are asking ourselves, what is it made up of? Quality means what? How well? How well? How well? But bring me to chemistry, we are asking ourselves, what is it made up of? What is it made up of? So, analysis, in analysis, we are trying to check something. We want to talk about analysis in chemistry. We are trying to check chemical analysis, we are trying to check what can we find there, how much of it can we find. So if we are doing a quantitative analysis, we are asking ourselves, how much of this substance can we find? But when we are doing a qualitative analysis, we are asking ourselves, what is it made up of? It's just like, for example, we have table salt. Table salt is NaCl, and we don't know that NaCl is present here. When we are doing qualitative analysis, we are asking ourselves, what is in this salt? At the end of the day, we could find that it is made up of sodium and chlorine. That's quantitative. What is it made up of? But when we are doing a quantitative analysis, we are asking ourselves, how much of this sodium do we have here and how much of this chlorine do we have here? So that's what is qualitative and quantitative analysis. So stoichiometry that we are looking at is a form of quantitative analysis. So we are asking ourselves, how much of this element we are interested in can we find in a certain substance or in a certain compound. So bringing down the definition for stoichiometry is simply defined as what we call mass-volume relationship. So we are going to take that definition as our final definition for stoichiometry. So let's take this down, and then we'll take the definition for stoichiometry. So stoichiometry, in its simplest form, like we said, this word comes from two words. I will use them. It's come from stoichion, and it comes from the word metron. And like I said earlier, stoichion here means element, and then metron here means measure. So bringing that down, the definition for stoichiometry is simple. So stoichiometry in its simplest form is defined as mass to volume relationship, or simply mass volume relationship. Mass volume relationship between elements, molecules, reactants, and products. So in our definition of stoichiometry, we define it as the mass volume. When we talk about mass, we are asking ourselves how much. When we talk about volume, we are also asking ourselves how much. That's why we said stoichiometry is a quantitative analysis. So in stoichiometry, most of the thing we are going to be doing is a lot of calculation, because we are asking ourselves how much. We are not asking ourselves what is it made up of. So to know how much, we must definitely calculate. That's why most students task stoichiometry to be a calculative aspect of chemistry. So now, what are the basic concepts we have in chemistry? We are going to take each of them one by one. So this stoichiometry 1, as we are going to look at the second aspect of stoichiometry in our next class. So we are going to look at this concept in today's class. So let's start this as stoichiometry 1, because we are looking at just this aspect of stoichiometry in this class. So the basic concept we have in stoichiometry, we are going to talk about what we call atomic mass, or in some other forms, we look at it as relative atomic mass. We also have molecular mass, and then we have relative molecular. This should be molecular mass, not atomic. So this is relative molecular mass. Then we are going to talk about what we call formula mass. We look at molar volume of gases. We are going to look at percentage composition, and lastly, we look at empirical and molecular formula. So let's begin by looking at atomic mass. Now, what's an atomic mass? If we take this word from the back, it means mass of an atom. So atomic mass from the back simply means mass of an atom. Again, what's an atom? That leads us to another question. So what's an atom? An atom is simply defined as the smallest and indivisible part of an element. So from the old time definition, it was defined as the smallest and indivisible part of an element. But later, there were certain experiments that were conducted, like experiment from J.J. Thomson, experiment from Lord and Rutherford. This experiment now showed that an atom can further be divided. But when we talk about an atom from the old definition says that an atom is the smallest and indivisible part of an element. So this was the old time definition for an atom as given by John Dalton. So this definition was given by John Dalton. But later on, this definition did not hold, because when we talk about an atom comes from the Greek word which is called atomos. And atomos in Greek means indivisible. So in the earliest time, John Dalton believed that an atom cannot be divided. So just like we have a piece of paper and we cut that piece of paper, there will be the smallest and tiniest portion which we cannot divide further. So that smallest portion is what John Dalton referred to as an atom. So that's why he defined as the smallest and indivisible part of an element. But when they conducted some experiments further, some other scientists like Lord and Rutherford, Sir J.J. Thomson and the rest, when they conducted some experiments, that you can even divide an atom further. And what are those things you get? We'll get what we call proton, electron, and neutron. So for short, this is called pen. For me, I refer to it as pen, P-E-N. So together, they are all called the subatomic particles. So they are called the subatomic particle. So now let's bring that back to our first concept, which is atomic mass. Again, atomic mass, like I said, simply means the mass of an atom, simple. So we have an atom, that smallest portion. What is the mass of that smallest portion is what we refer to as an atomic mass. Now, what is relative atomic mass? What is the difference? Why atomic mass? Then why relative atomic mass? Now, this is the difference. When we talk about relative simply means comparing one thing with another thing. So just like we have two friends, A and B. Now A got 60%, and let's just assume, okay, let's say we have just one student in a class, let's say John, and John got 60%. John cannot tell if he's intelligent than somebody or if he's not intelligent than somebody else, because he's just the only one, so we can't compare. But now when we have two students, John and let's say Bisola, and John got 60%, and then Bisola got 40%. John can now say that he's intelligent than Bisola based on their scores. Now, what is he doing? He can make that comparison because there's somebody else he can look up to. So for him, there's like a standard. I got 60 and she got 40, so I am better than her. You get that? So when we talk about relative here simply means a comparison. So what are we comparing with? We are comparing with a standard, and that standard in chemistry is what we call the carbon-12. So in your exam, they could ask you, the standard mass is what? The carbon-12 atom. So it's the carbon-12 atom. So the carbon-12 atom has a mass which was known already from calculation and a whole lot of experiments. So now, when they started discovering other elements that we have, like hydrogen, helium, lithium, beryllium, and the hundreds of elements we have, they now started using carbon-12 as a standard. Just like, for example, carbon-12 has a mass of approximately 12. And I found out that a substance is 2 times heavier than carbon. Immediately, I can see that, oh, that element has a mass of 24. So if I weigh that substance and I found out that, oh, this element is 2 times heavier than carbon, it will tell me that it is 24 gram of that substance. So now let's look at it in this slide. Let's look at it in a more easier form. So again, I said when you talk about relative simply means comparison with something, and you can only compare when there's a standard. You cannot compare when there's a standard. So let's say when we talk about relative, we already understand what atomic mass is. And atomic mass is just simply the mass of an atom. When we now talk about relative atomic mass is now the mass of an atom compared to the mass of carbon-12 atom. That's how it is defined. So this is simply the mass of an atom mass of an atom compared to the mass of carbon-12 atom. Like I told you, carbon-12 here is a standard. So the mass of carbon-12 is known to be approximately 12. So when we have a substance, we can compare the mass with carbon-12. So if we find out that, oh, that substance is like 2 times heavier than carbon, 2 times 12 will give us 24. So without calculation, I know that the atomic mass for that element, let's say for the element X of X, for example, will be what? 24. So we can make that comparison because we know this standard, which is carbon-12. So if I found out that an atom is like half of carbon-12, I can tell that that atom will have a mass of 6 grams. So that all comparison is made with what? Carbon-12. So when we talk about relative, we are comparing it with something. So now in exam, this is what we usually denote as A arrow. So relative atomic mass is denoted with what? A arrow. So in exam you see A arrow, and most times in your exams you are given. So for those persons that have studied their chemistry a lot, you see that in your exam they'll give you a substance in a bracket, right? ROAM. ROAM stands for relative atomic mass, or in some cases they'll put A arrow. So that's also the relative atomic mass. So for most exams you are given, but this is my advice for students: try to memorize some basic relative atomic mass, because in some exam you may not be given and then you are stopped if you don't know it. There are some basic elements you should know, like carbon, hydrogen, oxygen, nitrogen, sodium, sulfur, and the rest. In fact, your first 20 elements, I always advise you know their relative atomic mass in the case you are not given. But for exams like Waec, you most likely be given in a bracket. So we'll talk about relative atomic mass. So there's basically no calculation on this first aspect. So please, if you have any question, any comment or suggestion, please do it to leave them in the comment section beneath this video lesson. So we'll look at the second case, which is what we call molecular mass. So we have molecular mass. So when we read it from the back, it's simply the mass of a molecule. Again, we have another question: what is a molecule? So what is a molecule? A molecule is simple. A molecule is simply a combination or a constituent of what? Atoms of what? Elements. So simple. So let's take down that definition. So the next we are going to look at is molecular mass, before we now talk about a relative molecular mass. So let's talk about a molecule. So a molecule is a combination, simply put, it's a combination of atoms. The combination of atoms of elements. The combination of atoms of elements. So that's a simple definition of a molecule. So what about molecule? Just combination of atom of element. Now this element could be the same or it could be of different elements. Now let me show you a good scenario. Now if we have H like this, we call this hydrogen atom. Hydrogen atom. But when we now have a combination of it, let's say 2 hydrogen atoms joined together, we now have like this H2. This is no longer an hydrogen atom, but this is now a molecule of hydrogen gas. Molecule of hydrogen gas. Molecule of hydrogen gas. So gases exist as what we refer to as a diatomic nature. So gases are diatomic. Diatomic means 2 atoms will come together. Diatomic. Di means 2. Atomic, 2 atoms. So to tell that gases exist in a diatomic state. For example, oxygen, you see oxygen as O2. You see chlorine as O2. So all these ones, they are gases. So most gases, as you rightly say, exist in a diatomic state. So this is what we refer to as a molecule. So we have an atom. When we now combine atoms together, we eventually get a molecule. Also, this is a molecule of oxygen gas. This is a molecule of chlorine gas. But when I give you O, this is oxygen atom. Then when I give you Cl, this is chlorine atom. So take note of the difference between an atom and a molecule. Now, when we talk about molecule, like I said, it's a combination of elements. This element could be the same or they could be different. Different in the sense that we have water. This is H2O. This is a molecule of water or water molecule. This is a molecule of water. So why is this a molecule? Because their atoms are joined together. Here we have hydrogen, then we have what? Oxygen. So we have joined this hydrogen atom with this oxygen atom. So we have combined these atoms together. So take note, molecule is just simply a combination of atoms. Now going back to our definition, so what about molecular mass? We are talking about the mass of a molecule. So already we define molecule and you understand what it means. Next, relative molecular mass is simply just the mass of a substance compared with the standard. And what is standard? The standard is 1 mole of that substance. 1 mole of the substance. So 1 mole. Just like, for example, whenever you want to buy a crate of egg contains 30 eggs. So the standard is just a crate. So if I tell somebody, in this bag there are 60 eggs, that should tell me that will be what? 2 crates. Why can I say it is 2 crates? Because it's a standard. And what is standard? That's 1 crate of egg. Do you get now? So the standard is just 1 molecule of the substance. So we are comparing the mass of that substance to 1 molecule. So that's what a standard simply means. Just like we say a dozen. A dozen means 12. So 1 dozen means 12. And then if someone comes and tells me that in a bag there are 24 of that substance, I should tell that there are 2 dozens. Why can I tell that there are 2 dozens? Because I know that the standard tells me that 1 dozen is equal to 12 of that substance. So relative molecular mass is simply the mass of a molecule of that substance compared to 1 molecule of that same substance. So that's what we mean by relative molecular mass. Already we know what molecular mass is. They're relative. We are comparing it with 1 molecule of that substance. So, but let's look at there's a calculation for this. We are going to look at how to calculate molecular mass or relative molecular mass. Now, when we talk about relative molecular mass for both of them, let's take a single definition for the both of them. So let's take a single definition for the both of them and then we proceed from here. So I'm going to take this off so that we can do some calculation. So we are going to talk about molecular mass and relative molecular mass. So I'm going to take this off the board because we have looked at them. So now let's talk about relative molecular mass. So definition. So for molecular mass is simply the sum of the relative molecular mass of the relative atomic mass of the atoms present in the molecule of that substance. So this is our definition for molecular mass or relative molecular mass. So it's very basic. We are looking at the sum of all the masses. So it's just like I have a bag. So I have a bag. And in this bag, there are, let's say, 2 balls. We have a big ball, which is 2 kg. We have a small ball, which is 1 kg. So these are atoms. But when we pair them together, it will form these bigger balls, which is a molecule. So this is an atomic mass, this is an atomic mass. But together, when we sum them up, 3 kg will be the molecular mass. So we are going to calculate the molecular mass of certain substances. So let's take down. So let's look at this example. So example, in your exam, you could be told to calculate the relative molecular mass of, so let's take this example. So number 1, we are going to do that for H2SO4. So number 2, we are going to try water. Number 3, we are going to try CaOH2. Then lastly, we are going to try, let's try HNO3. Okay, so we are going to calculate this relative molecular mass and see how it is done. So let's start with, good, in your exam, you'll be given their atomic mass. But like I said, if you are not given, it is very, very ideal you memorize some, especially in exams where you might not be given, like UTME for some certain schools. So let's take the relative atomic mass. For hydrogen, it is usually 1. For sulfur, it is 32. For oxygen, it is 16. For calcium, it is 40. What else do we have? We have nitrogen. For nitrogen, it is 14. This is calcium, not carbon. Then do we have carbon? Okay, we don't have carbon. Carbon is 14. So now let's calculate. Now pay attention. Let's start with this compound, which is tetrazol sulfate 6-oxy. So for H2SO4, so we have H2SO4. Now, this H2 means that we have 2 atoms of hydrogen. 2 atoms of hydrogen. This S is just a 1. There's a 1 here, even though it is not written. So we have 1 atom of sulfur. Then 4O means we have 4 atoms of oxygen. So now, already 1 atom of hydrogen is just 1 gram. But we have 2 of it. So what are we going to have? We are going to have for this is going to be 1 times 2 because we have 2 of it. Plus the next is sulfur. Sulfur is just 1. So 1 atom of sulfur is 32. Plus oxygen, 1 atom is 16. But we have 4 atoms of it. So I'm going to say 16 times the 4 atoms we have. So this is what we are going to do. So we are simply going to calculate. Now 1 times 2 will give us 2. So this is 2 plus, now, or let me write it up there. So 1 times 2 here will give us 2 plus this is 32 plus this is 16 times 4 will give us 64. Now we are going to add this up. So this will be 34. 34 plus 64 will give us 98. So this is 98. Now there's a unit for molecular mass, but there's no unit for relative atomic mass. But they are the same. So for molecular mass, unit is usually gram per mole. But for relative molecular mass, there's no unit. So if, for example, you solve and you get 3, if you are talking about molecular mass, I'm going to write it as 3 gram per mole. But if I'm talking about relative, it's just 3. So when I talk about relative, you don't have, because it's just like you are comparing one thing with another thing. So it's just like if I have 4 kg over 2 kg, kg will cancel kg. So basically, there's no unit. So whenever you hear the word relative, just know that there's no unit for it. So in this case, if you are calculating molecular mass, this will be 98 gram per mole. So the unit for molecular mass is gram per mole. So that's in gram per mole. But if it were to be relative molecular mass, it will simply be 98. So take note of that disparity. So let's look at the next one, which is water. We are going to calculate the molecular mass for water. So for number 2, we have water. Water is H2O. Now for water, if you look at it closely, we have 2 atoms of hydrogen and then 1 atom of oxygen. So for this 2 atoms of hydrogen, it's going to be 1 times 2 plus, because we have 2 atoms of hydrogen. Then for oxygen, we have 1 atom of oxygen. So we are simply going to write that 16. So 1 times 2 will give us 2 plus 16. And 2 plus 16 will give us 18 gram per mole. Since we are calculating for molecular mass, this will be 18 gram per mole. But if you are calculating for relative molecular mass, it's simply going to be 18. Take note of that for the purpose of exam. So let's look at the third one, which is calcium hydroxide. So we have calcium hydroxide and it's written as CaOH2. Now I love this compound because most times some students would throw away the 2 because they feel like, oh, it's not really important. But it's very, very important. Now let me tell you something you ought to know. When you see a compound like this, for me I like to expand it. It makes more sense. Now there's 1 here, there's 1 here. So if we expand this, we are going to have Ca. 1 times 2 will give us 2, so it's going to be O2. Then 1 times 2 give us H2. Now why am I doing this? Because these 2 affect everything in the bracket. So the 2 affect both the oxygen and the hydrogen. Take note of that. That's why I said 1 times 2. If I had 2 here, for example, 2, I'm going to say 2 times 2, I'll be having 4 here. But since it's a 1, it's going to be 1 times 2, 2, 1 times 2, 2. So we can now go ahead and calculate. Now for calcium, the relative atomic mass for calcium is 40. So this is 40 plus oxygen. We have 2 atoms of it. So it's going to be 16 because 1 of it is 16. But we have 2 of it here. So it's going to be 16 times 2 plus, for hydrogen, we have 2 atoms of hydrogen. But 1 atom of hydrogen is 1. So this is going to be 1 times 2. So now we are going to calculate. Now this is going to be 40. So let's take this on the board and then calculate. So this is 40. This is 32 then this is 2. Then this plus this will give us 72 plus 2. Then our final answer will be 74 gram per mole. Remember, if it is molecular mass, we can end in gram per mole. But if it is relative molecular mass, it's simply going to be 74. Then the last compound we have here is triazononitrate 5 acid. That's what we call HNO3. So for the fourth one, we have triazononitrate 5 acid, or you can also call it nitric acid. Now this HNO3 means 1 atom of hydrogen, 1 atom of nitrogen, then 3 atoms of oxygen. So let's go. For H, this is going to be the mass of hydrogen atom is 1. So this is going to be 1 plus nitrogen is 14 plus oxygen is 16. But we have 3 atoms of it, so that will give us 16 times 3. So we have this will be 1 plus 14 plus this will give us 48. So let's add up. This will be 15, then plus this will give us 63. So final answer will be 16 gram per mole. So this is how we simply calculate molecular mass or relative molecular mass. The difference lies in their difference in definition and just how it is used. So the next one we are going to look at is formula mass. Now, we are not going to clean this question because for a reason. Now, sometimes we also call molecular mass formula mass, but what's the key difference? We use formula mass for what we call ionic compound. So take note of that. We use formula mass for what we call ionic compound. So formula mass is simply the mass of ionic compound, and also it has no unit. So now some people might wonder, or they might ask, what is formula mass? Very good question. What is the formula? So it was an ionic compound, because we've already broken down the definition of formula mass. It is the mass of a formula, but what was that formula? An ionic compound. Now, what's an ionic compound? Now, in chemistry, we have what we call ionic compounds. Now, ionic compounds are formed mostly between metal and non-metal, or we can say whenever a metal gives out electron and a non-metal receives electron. So we form an ion due to a transfer of electron, usually from a metal to a non-metal. So just like, let's understand this case of ionic in a very simple way. Now, ionic is just like, in nature we have boys and then we have girls, for example. Nature has patterned it such that they believe that, or let's say fathers and mothers, father, mother, and children. So nature has patterned it in a way that men should always give to women. That's the way nature has patterned it. So male is just like a metal, then females are like non-metal. So when there is a transfer of electron from a metal to a non-metal, compounds that are formed in that process is what we refer to as ionic compounds. Now, this compound, that's why we have what we call this compound contains what we call an ionic bond or electrovalent bond. So take note of this. Ionic compound contain what we call ionic or electrovalent bond. Electrovalent bond. That is why this bond is defined as that bond that is formed when metals transfer or donate electron to a non-metal. So now, example of compound we have are NaCl. For example, NaCl is an ionic compound. Now, when you get to see how this compound is formed, you understand that sodium loses one electron to chlorine, then chlorine gains an electron. So ionic compound is formed when an atom loses electron to another electron to form a certain compound. So let's just take NaCl as an example and then calculate for NaCl. So let's take that as an example and then we'll do it to calculate. So now for NaCl, what we have is, now I'll just explain this again so that majority of persons that are watching this video right now will understand this concept in depth. Now, ionic compound is simple. An ionic compound contains an ionic bond, or we call it an electrovalent bond. And that bond is formed when there is a transfer of electron. Like I said, just assume a male and a female. There's a transfer of electron from the male to the female, but not male in this case, a metal to a non-metal. So we have sodium, this is sodium atom. But when sodium loses an electron, it becomes Na plus. Then chlorine, this chlorine, normal chlorine gas, when it gains an electron, it becomes chloride ion, Cl minus. So when these two guys come together, they will form what we call NaCl. So in addition, there's a plus here and there's a minus here. So again, another simple way to know it is that when we say ionic, ion are atoms that are charged. So you are going to see charges. So those kind of compounds is what we call ionic compound. And the mass for such compound is what we call a formula mass. Now, one unique thing you should know is that formula mass has no unit. So let's calculate for the mass of sodium chloride. Now, sodium, the mass is 23. The relative atomic mass, like I said in the example, give you in brackets, Na is 23, then chlorine is 35.5. Now this 23, then chlorine is 35.5. And then when we add this up, we are not multiplying because we have one atom of sodium and one atom of chlorine. So just write them out. So when we add up that, we are going to end up getting 58.5. Like I said, there is no unit for formula mass. So we've talked about three interesting concepts. We've talked about atomic mass or relative atomic mass. We've talked about molecular mass or relative molecular mass. And also we've talked about formula mass, which we said is the mass of any compound and it bears no unit. So we are going to move on to our fourth concept, which is mole. So we're going to talk about mole. And it's also a very interesting concept. Mole. We keep talking about mole. But what was mole? Let's go. So before we talk about mole, if you are just joining this live video, please do it to give this video a thumbs up. And if you have questions, comment, or suggestion, please do it to leave them in the comment section beneath this video lesson. And also, if you are new to this channel, if you are just coming across this video for the very first time, or this channel in particular for the very first time, please do it to hit the subscribe button, and also so I can get access to my wonderful videos. So let's proceed. So we are going to talk about a mole. Now, what's a mole? A mole is a very interesting concept, like I said earlier. In physics, they will tell you that it is one of the 7 fundamental quantities. And what is that quantity? Amount of a substance. So they will classify it as the amount. So it is being classified as amount of a substance. And in physics, you'll be told that the amount of a substance is measured in what we call mole. So today we are talking about this mole itself. Now, what's mole? Now, mole is just like having a crate of egg. Now, when you have a crate of egg, I know that for every crate of egg can take 30 eggs. Simple, nothing more than 30 eggs. So a crate, when you are told that, oh, there's a bag here, and in this bag, there's 1 crate of egg, I know that there are 30 eggs. If I'm told that there are 2 crates of egg in that bag, I know that there are 60. If I'm told that in this bag, there are 3 crates, I know that there are 90 eggs. So we can tell because we know that 1 crate of egg will always contain 30. So that pattern of grouping substance together in chemistry is what we call mole. So either we are grouping atoms, we are grouping particles, or we are grouping molecules together. So that pattern is what we call mole. So what's a mole? Now a mole is defined. So let's take that. A mole is defined as the chemical, as the amount of a substance, which contains a particular number. Like we said, 1 crate of egg is 30, or 1 dozen is 12. Now 1 mole contains 6.02, there's a decimal point here, times 10 raised to power 23 particles. Now these particles can be anything. These particles can be ions, these particles can be atoms, these particles can be molecules. So, and this number here is what we call the Avogadro number. Avogadro's number. In our 3rd class or in the 2nd class, we talk about the Avogadro's law. So the Avogadro's number is what we refer to as 6.022 times 10 to the power 23. Again, I will urge students, if you are watching this video currently, it is very important you memorize this. It's a constant. You memorize this number. It's a constant. It's 6.022 times 10 to the power 23 particles. That particles, if you are talking about ions, is 6.02 times 10 to the power 23 ions. If you are talking about atoms, times this number atoms. If you are talking about molecule, this same number molecule. So now the basic thing is that how we calculate. So we are going to do a calculation. Now, another thing is that, like we said, 1 mole of every substance will contain this. So let's take a question. Let's take this question. Example. Now, beyond this, just beyond this, I'll just remind you of a formula which we've looked at before, which majority of persons watching this video right now should know. Now, there's a formula for mole. Beyond this formula, we also know that. Okay, I'm going to give two formulas before we take an example. So let's just look at this formula. So this formula, we have this. So two formulas under this part. So formula. So the first one I'm going to look at is that particles, whatever the particles may be, and I told you that particles can be ions, can be atoms, can be molecules. So that particle is equal to mole of the substance times 6.022 times 10 to the power. Let me take this off. But please know that this is what we refer to as Avogadro's number times 10 to the power 23. So this is one formula. Then secondly, mole itself is calculated as reacting or the given mass over the molar mass. So two important formula for calculating question related to mole. Now, particles is equal to mole times 6.022 times 10 to the power 23. Then this mole itself can be calculated as reacting or giving mass over what molar mass. Now let's take a look at how we can use this formula. So let's take a question. Let's say we are given this. So okay, I'll take this off the board so that we can understand this topic. Remember, a mole is what? The amount of a substance which contains, we just reversed it, is the amount of a substance which contains 6.022 times 10 to the power 23 particles. Again, particles can be ions, can be atoms, or can be molecules. Now, this number, like I said, is what we refer to as Avogadro's number. And the formulas are this. We have particle is equal to mole times this number, Avogadro's number. Now, we have mole itself, which is reacting or giving mass over molar mass. So we are going to take a question. We understand this thing in a very detailed concept. So let's take this question. So we have a question. So let's say we give me example. So this is a question we are going to look at just to understand what mole is, so I can basically understand the formula we looked at. The question says there are two in one. This is a 2-in-1 question. It says calculate the mole and the particles that are present in 36 grams of water. Now, for 36 grams of water, we are given a mass of water which is 36 grams. The first part says calculate the number of moles. So I'm going to look at that part first. Now, how to calculate moles? So for the first question, we know that mole is equal to reacting mass or the given mass over the molar mass. Now in your exam, you could be given this, but like I told you, please do it to memorize it. O is 16. So that's what we are going to look at. So the reacting mass, we are given in question, or like I said, given mass, which is 36 grams. But for a molar mass of water, we have to calculate for it. So let's quickly do that. So molar mass of water, molar mass, this MR of water, will be, now we have 2 atoms of hydrogen, so this is going to be 1 times 2 plus 16, and then this will give us 18 gram per mole. Now for the mole, so the mole will be equals to the reactive mass, which is 36 gram, over the molar mass, which is 18 gram per mole. And then when you divide 35 by 18, will give us 2 moles. So in this mass of water, there are 2 moles present. It's ideal. If 1 mole is 18, meaning 2 will be 36 gram. Now, so the second part says calculate the particles, and I gave you a second formula. Now we can solve this part in 2 ways, but let's use the formula. So for number 2, we know that particles is equal to moles times 6.022 times, or let's say 6.02 times 10 raised to the power of 23. Now, so the particles in this case will be the number of moles which we have calculated for. So if we are told to calculate the particles straight, we will still have to calculate the moles first before you can come back here. So this is going to be the moles, which is 2 times 6.02 times 10 to the power 23. Now when we multiply this times this, we are going to end up getting 12.04 times 10 to the power 23 particles. So this is going to be the final answer. So that's one way we can solve it. Another way we can solve it is that we know that 1 mole we contain, like I said, 1 mole of every substance will contain Avogadro's number. What's Avogadro's number? 6.02 times 10 to the power 23. But in this case, we have 2 moles. So 2 moles will be equals to what? X. Then we are going to cross multiply like we do in math. Then 1 times X will give us X. There's going to be 2 times everything up here. So that's going to be 2 times 6.02 times 10 to the power 23. Again, when we multiply, this will give us 12.04 times 10 to the power 23 particles. So that will give us 12.04 times 10 to the power 23 particles. So I hope you understand this aspect. So with that being said, we are going to move to the next concept, which is molar volume of gases. So let's take a look at that. So our 5th concept here is the molar volume of gases. So molar volume of gases. So what we are going to look at next is molar volume of gases. So our 5th concept is molar volume of gases. So now what about molar volume of gases? Without wasting time, molar volume of gas simply means the volume of 1 mole of every gas. So we looked at this concept when we talked about gas laws. So when we talked about standard temperature and what pressure. So now this simply it is the mole, it is the number of moles of a gas. So it is the volume, rather, it is the volume of a gas under standard temperature and pressure. Under standard temperature and pressure. Understand temperature and pressure. So like I said in one of our videos, standard temperature is what we refer to as what? STP. So understand temperature and pressure, 1 mole of every gas will occupy a volume of 22.4 dm3. So at STP, and we know what STP stands for, standard temperature. Standard temperature is what? 273 Kelvin. And the standard pressure is 760 millimeters of what? Mercury. So under these 2 conditions, 1 mole of every gas, 1 mole of every gas, it does not matter if it is hydrogen or if it is chlorine, every gas you can think of, 1 mole of every gas, provided it is under standard temperature and pressure, and it is 1 mole of that gas, we occupy a volume of what? 22.4 dm cube. So this is also equal to 22,400 cm cube. So in dm cube, it is 22.4 dm cube, but in cm cube, 22.4 dm cube. So it's simple. At standard temperature and pressure, on standard condition, it's just like you have a box, a normally shaped box. You know that, okay, this box can always take 10 packs of biscuits. So in a standard condition, that pack should take what? That box rather should take 10 packs of biscuits. So at standard temperature and pressure, every gas will occupy a volume of 22.4 dm cube or 22,400 cm cube. Now, something that is also very important, which we call room temperature and pressure, so we call that RTP. So this is what we call room temperature and pressure. Room temperature and pressure. So room temperature is usually a range between 20 to 25 degrees Celsius, and room pressure is usually at 1 atmospheric pressure. So under these two conditions, the molar volume of a gas, molar volume of a gas is 24 dm cube. Or in cm cube, that's going to be 24,000 cm cube. So take note of this. So, but basically for the JAMB and Waec examination, it's good to understand what we call standard temperature and pressure. At STP, 1 mole of every gas will occupy a volume of what? 22.4 dm cube or 22,400 cm cube. This could likely be an objective question. So that's a very basic concept. So let us take a question. So let's take this question. So I'll take room temperature and pressure off the board. But just know that the value of molar volume of every gas at a room temperature and pressure is 24 dm cube. So let's say we have an example. So the example, let's say we are told to calculate the volume of 140 gram of chlorine gas at STP. So this could likely be a question in an exam. Calculate the volume of 140 gram of chlorine gas at STP. Now, provided you are told that STP, you will keep working with 22.4 dm cube. So now let's go. So let's take a look at that one. So since we are told that we are looking for volume at STP, your mind should first go to the fact that 1 mole of every gas at STP will occupy a volume of what? 22.4 dm cube. So this should be the first thing you should think of. Now, we were given the mass of chlorine gas, but we don't know the mole. So we now have to calculate for the mole. Now, remember I told you that mole is equal to reacting mass or the given mass over what? Molar mass. So this is the formula I gave to you earlier. Now, a gas, like I said also in this video, I said every gas usually exists, or most gases exist in a diatomic state. Chlorine gas will be seen like Cl2, not just Cl. Gases are usually what? Diatomic 2. Now, in a bracket, let's take this. Chlorine is usually 35.5. Now, the reactive mass given to us in this case is 140 grams. But we don't know the molar mass, so we have to calculate. So let's calculate from here. This chlorine, we have 2 atoms of chlorine. So it's going to be 2 times 1 mass is normally 35.5. So this is 35.5. So 2 times 35.5 will give us 71 gram per mole. So this is 71 gram per mole. So we are going to calculate the mole. So now the mole, because of the reacting of the given mass, and the given mass in this case is 140 gram. So we have 140 gram divided by the molar mass, which we just calculated for, just now to be 71 gram per mole. So we are going to divide that and get our final answer. So we are going to divide 140 by 71. So this will give us 1.97 mole. So this is going to be 1.97 mole. So that's the number of mole present in 140 grams of chlorine gas. Now again, we are just going to establish the fact that 1 mole of every gas will occupy a volume of 22.4 dm cube. But in this case, what we have is 1.97 mole. So 1.97 mole will be equals to what? X. So we are going to cross multiply. Now 1 times x is x. Then we are going to multiply this times this. So that will be 1.97 times 22.4. So we are going to multiply that now. And this will give us 44.17. So therefore, final answer is 44.17 dm cube. So this is in dm cube. If we are told to leave the answer in cm cube, we multiply by 1000. And when you do so, we are going to have 44,170 cm cube. So that will be your final answer, either in dm cube or in cm cube. But the idea is usually in dm cube. So we've talked about those several concepts from atomic mass or relative atomic mass, molecular mass or relative molecular mass. We talk about formular mass, we talk about mole, we talk about molar volume. So now we are going to look at the last two aspects, which are percentage composition. Then empirical molecular formula, we've talked about that concept in our very first video. So you can go back and check the first live video we took on empirical and molecular formula. So we are going to talk about percentage composition, which will draw this class to a close. So let's talk about percentage composition. So we are going to talk about percentage composition. Percentage composition. So percentage composition. Now I want to talk about percentage composition. What do we really mean? It's just like there is a class now, for example. There's a class of, let's say, 50 students. So we have 50 students. 50 students. Now, out of these 50 students, let's say we have 25 boys and then we have 25 girls. 25 girls. So this class is composed of boys and girls. So when they ask us percentage composition of, let's say, the boys, it's going to be the number of boys, so that's 25, over the total, which is 15. So we have 25 out of 50. Since it is percentage, it's going to be times 100. So this will give us 50%. So it means that the class is made up of 50% of this number of students composed of 50% of boys. Then same thing for the girls. That will be 25 over 50 times 100. This will also give us 50%, meaning the girls make up 50% of the class. The same thing applies to percentage composition. When we have a molecule, let's say for example, we have H2SO4. H2SO4. Hydrogen has its own composition in this entire molecule. Sulfur has its own composition. Oxygen also has its own composition. Then how do you calculate for percentage composition? So the formula is the most important thing to us. So for percentage composition, this is the formula. Percentage composition. Percentage composition is equal to mass of the element. Mass of the element over the molecular mass times what? 100. So this is the formula we need to calculate the percentage composition. So mass of that element you are interested in over the molecular mass, that's the mass of the entire molecule, times 100, because we are expressing it in percentage. So we are going to take a look at some examples just to understand this concept properly. So let's take a look at some certain examples. So let's take a look at this. So example, calculate calculate the percentage composition of the underlying element. We are going to take a look at 4 examples. So question 1, we are going to take a look at H2SO4. So we are going to underline S. Then we are going to take a look at number 2. We are going to take a look at CaCO3, and then we underline this. Then for number 3, let's take a look at HNO3. Okay, we are going to take this. And then in our 4th example, we are going to take a look at let's take a look at let's take a look at Na2, or let's take a look at a compound that has a bracket. Okay, let's take a look at calcium hydroxide again. So we are going to use this for example. So we are calculating the percentage composition of, let's take calcium in this case. So we are going to take a look at this for example, just to understand what percentage composition, or how to calculate for percentage composition. Again, the formula is simple. So the percentage composition, so this is we are calculating percentage composition of sulfur. So let's say percentage composition of sulfur will be the mass of the element. What the element we are interested in? Sulfur. And just to know, okay, I'm going to give the masses here. So for hydrogen it is 1, for sulfur it is 32, for calcium it is 40, for oxygen it is 16, then we have nitrogen, which is 14, and I think that's all. Okay, carbon, we have carbon as well. So carbon is 14. So that we can. Now for the first composition of sulfur, in this case, the mass of the element we are interested in sulfur. So the mass of sulfur here is what? We have just one atom, and sulfur is just 32. So this is going to be 32 over the total mass of this element. So this is 1 times 2. So this is 1 times 2 plus sulfur is 32 plus oxygen is 16 times 4 times 100, because we are expressing it in percentage. So we are going to do our calculation right now. So this is going to be 32 over, when we add up this, we are going to get 98 times 100. So we are going to do the calculation now. That's 32 divided by 98 times 100. That will end up giving us 32.65%. So the final answer here is 32.65%. So this is how you calculate percentage composition. So it is the mass of that element you are interested in over total mass of all the elements times 100. So let's take a look at the second one, which is CaCO3, that's calcium triazocarbonate 4. So we are interested in the percentage composition of carbon. So percentage composition of carbon will be the mass of the element. And what's the element in this case? Carbon. And we have just one atom of carbon, and carbon is 14, over the mass of the entire molecule. Calcium here is 40, that's calcium 40, carbon is 12, 14 rather. Oh, sorry, this is not 14, this is 12. Carbon is 12, not 14, so this is 12, this is 12, and then this is 12. So plus oxygen is 16 times 3 times 100. So this is going to give us 12 over, when you sum this up, you end up getting 100 times 100. So when you divide and multiply, you are going to end up getting 12%. So the percentage of carbon in that substance is 12%. So I hope that's clear. So we are going to look at the third example. If you have solved that, you can leave your answer in the comment section. Let me check. So we move to the third question. Our third question is HNO3, which we call trioxonitrate 5 acid. So now, how do we solve this? We are interested in the percent composition of nitrogen. So let's say percentage composition of nitrogen will be the mass of the element you are interested in, which is nitrogen, and that's 14, over total mass, which is the molecular mass, and that will give us H here is 1 plus nitrogen is 14 plus oxygen is 16 times 3 times 100. Now this will give us 14 over 1 plus 14 plus 48. So we have 1, this 14 plus 48 times 100. So we are going to do the calculation now. So that's 1 plus 14 plus 48, and that will give us 63. So I'm using 14. I'll be dividing 14 by 63. Then I'll multiply my answer by 100, and that gives us 22.22%. So the final answer here is 22.22%. So that's the final answer to the question. So then we take a look at the fourth question, which is calcium hydroxide. So we are interested in the percentage composition of calcium. So percentage, so let me demarcate, percentage composition of calcium. Or let me take this off. Of calcium. So the formula again is the mass of the element. And the mass of the element we are interested in. We are interested in calcium, and calcium is 40 over, now this is 40 plus, remember these 2 will affect everything in the bracket. So we have 2 times 1, which is 2, meaning we have 2 atoms of oxygen, but 1 is 16, so that's going to be 2 times 16 plus hydrogen is 1 here, but 1 times 2 gives us 2. So in total here we have 2 atoms of hydrogen, and 2 times this one here. So we are going to have 2 times 1 times 100. So this will leave us with 40 over, so let's check that. So that will be 40 plus 32 plus 2. And this will leave us with 74 times 100. So when we do that, our final answer will become 40 divided by 74 times 100, and that will leave us with 54.05%. So that's about 54%. So let's take the nearest whole number, 54%. So this is how we calculate 4 percentage conversion. So in percentage conversion, we are trying to look at what percentage does that element make in the entire compound or molecule. So viewers or dear scholars, I hope you have learned something from today's video lesson. So this is Stoichiometry 1. As our next class, we focus on Stoichiometry 2, where we are going to look at how to balance equations and how to use this equation to answer stoichiometric questions. So till you get to see the next class, do have a wonderful time.